scope to talk about whatever the hell I wanted to talk about. Does this work? Okay. Well, it's a great pleasure to be here in Madrid and at the IFT and to participate in the inauguration of this absolutely gorgeous building, which I gather still has space. So as director of the ITP, which is a similar name in English, for an Institute of Theoretical Physics, let me just warn you that there's the first law of buildings is that they fill up very quickly. And by next year at this time, I have no doubt that you'll be looking for more space. So keep some rooms empty under lock and key and don't tell anybody. This is good plans for the future, especially given the economic situation. So this has been an exciting conference, especially since on Tuesday, CERN, in celebration of the inauguration of the IFT, held a very exciting seminar in which they announced, in my opinion, the potentially, most likely, the discovery of the Higgs, which we just learned doesn't exist. Some weeks ago, a reporter from Nature called me and some others and asked, well, CERN is going to talk about the Higgs shortly. Do you believe, do you believe that the LHC will find the Higgs particle produced by the standard model of particle physics? So I answered this reporter, absolutely, and I explained in great detail why, I believe eventually, next year or so, the Higgs, some variant, most likely supersymmetric, will be found. 2 paragraphs. They took the word absolutely. They asked other people, and this, I thought you would be amused by the responses that were made by these leading so-called theoretical physicists before Tuesday. Tom Kibble said, in some ways I would prefer that it not be found. I don't think that was a scientific judgment, probably a personal judgment. Steve said, there are other possibilities. Steve is very cautious, always covering his bets. 50-50 down on the list of, on this list that was made. Shelley, you remember? You said, if not in 2 years, then never. Also, a very careful statement, you notice. He actually didn't answer the question. He made an absolutely correct observation. Lisa said, hopefully. That puts her sort of in the potential crowd. John Ellis said, as a fully paid up supersymmetrist, I have to say yes. Frank said, I remain optimistic. Oops, I didn't want to. Frank said, I remain optimistic, so he's counted as, you know how long it took to make this slide? I remain optimistic, which is a yes. And, for me, I was really upset because I wrote 2 carefully thought out paragraphs and they took the first word, absolutely, and put me at 5 sigma. So Tuesday was a great relief. I felt, wow, not bad, because I must say, personally, I don't understand why this room was so muted. I hear rumors that the group at Princeton, which got up at 8 a.m. in the morning, broke into cheers as Fabiola showed this plot. A 2.3 to 3.6, depending on whether you somehow take into account this fancy statistical method of looking everywhere from 100 GeV to 600 GeV in your estimate of the likelihood of such a bump. and you get 2.3 if you just take the data as shown. For something which, as Teeny reminded us, we've been looking for 3 decades. We know what it is. We know what the channels are. We know what the signals are. They've been analyzed. And the atlas, and Fabiola in particular, explained in great detail the analysis of the systematic errors, which was truly amazing. So, why don't we accept statistics? This is good evidence, not just for the Higgs, but for a Higgs which is in somewhat conflict with the standard model, instability. It's good for supersymmetry. It's good for all of us. This is exciting. We will know clearly within the next year whether this raises to the level that the incredibly rigorous and conservative level that we impose today on discoveries or confirmations of 3 decades old predictions. If you include all the data, as some people on the blog have done, this is now a 4 sigma bump. That's just including L8C, and all the existing data, somehow, not authorized by the experimental groups, and not taking into account, or just if you want, taking into account the LEE effect in the range that has not been excluded by this and other experiments. Okay, that's enough about the Higgs. I think Nemo will discuss later on today the implications of this discovery for our attempts to go beyond this incredibly successful theory we have. Now, it is depressing sometimes, as Teeny remarked, that we have a theory of elementary particles describing all of the subatomic forces that work so well, and that there are so few clues as to what lies beyond it. But it is also a remarkable achievement, and it is worthy of celebration over and over again. Such successes don't happen often in the history of science. It really works. Not just in the electroweak sector, but in the strong sector as well. This is an old plot from this summer of the dijet cross-section that, as predicted by QCD. But they're now, that's only with 0.7 inverse femto point, or 0.8. By now, the tests of the standard model in all of its aspects are incredible. But we know that there's physics and life and questions beyond the standard model. And aside from just the interest of doing something important and fun at the new IFT building, this is what pushes us forward. There are experimental indications, clearly, that we must go beyond the standard model to understand dark matter, the only form of matter really discovered by astrophysicists so far. Neutrino masses, baryon asymmetry, we still do not understand, although maybe that's just a theoretical problem. And of course, the cosmic acceleration. And then there are theoretical puzzles that us theorists think we should be able to understand, such as the unification of those 3 Maxwellian-like forces, which at their heart are all the same and fit together so beautifully together with the matter multiplets. The hierarchy problem, or the electroweak scale, compared to the unification or Planck scale. The flavor masses, mixings, generations, total mysteries. Shelley described, but with no real idea, no success. And of course, cosmology, which is now a quantitative science and gives us mysteries that we must explain. To me, among these clues, experimental and theoretical, the ones that have pointed in a fascinating new direction is supersymmetry, and motivated, well, phenomenologically motivated by these three fundamental problems: observational and theoretical. And supersymmetry, invented for other reasons, first discovered in string theory, beautiful extension of ordinary space-time and its symmetries to allow for quantum dimensions, naturally gave explanations, or gives explanations, potential explanations for these problems. It's a very compelling case, which is, of course, why it is one of the main foci of the experimental program at the LHC. It is beautiful and predictive. Supersymmetric models have dozens and dozens of parameters, but they're all in the symmetry breaking sector. The theory as itself, just take the supersymmetric model, make it supersymmetric, has no new parameters. That's incredibly predictive. Of course, the symmetry is broken, and there we have many ideas, many models, and many parameters. And there's nothing beautiful about our attempts to break the symmetry, which one could say also about the Higgs sector. What we've learned so far from the LHC is that colored particles are not around the corner. Those are the ones we would have seen immediately. Many models predict, and some of phase space has been ruled out, especially that we would have seen these colored particles. Now let me turn to the other reason why I love supersymmetry, not just phenomenology, and the answer to those three important problems, but as a theorist. Anyone who has studied supersymmetry, and with all the developments of especially the last decade, cannot relinquish this. It's like Einstein said about his theory when confronted by experiments that seem to contradict it. He can't believe that nature would not have taken advantage of such a beautiful structure. In using supersymmetry, and in recent years, I believe we have found finally a wonderful playing ground for theorists, what might be called the hydrogen atom of quantum field theory. The hydrogen atom, or in general, the 1 over r squared system of two particles, played an incredibly important role in the history of physics. This was an integrable theory with enough symmetry to allow one to write down a simple, complete solution, which was a good approximation to the real world. And it, of course, we are very lucky that such a simple integrable system played such an important role both in gravity and in the motion of the Earth around the Sun, which is the good approximation given by this integrable system, and, of course, in the case of the hydrogen atom. If Newton didn't have such a simple integrable system to start with, it would have been much harder to develop the laws of classical mechanics. And certainly the Bohr model, which happened to be an exact solution to the hydrogen atom using a semi-classical approximation to a theory which wasn't known, was exact because it was an integrable model. And that enabled Bohr to make the crucial step that led to quantum mechanics, to understand the periodic table, and eventually to, within a few years, within a decade, to the greatest revolution, I think, that physics has gone, that of quantum mechanics. Also the Dirac equation and its simplicity, which motivated relativistic quantum mechanics and quantum field theory. We were lucky to have the hydrogen atom, an integrable model, which, to a very good approximation, since the fine structure constant is small, approximated the real world. In two-dimensional model field theories, we've had a galore of integrable models, which have played a crucial role in our understanding both of quantum field theory, its renormalization, normalization group, anomalies, and many other features of quantum field theory. But in 4 dimensions, until recently, that's been lacking. However, gauge theories, which play a big role in the standard model, cannot be really tackled. Even QCD, which has sort of no parameters, and for large momenta is a simple theory. For small momenta, strong coupling is intractable except by numerical techniques. On the other hand, we seem to have found in the supersymmetric, maximally supersymmetric cousin of QCD, with maximal maximal supersymmetry, a integrable model. Similar to the hydrogen atom, perhaps. Not as close to nature, of course. And so the n equals 4 supersymmetric gauge theory with an infinite number of colors, and the first step in an approximation to this quantum field theory in 1 over nc is, it is believed with great certitude, integrable. There are an infinite number of conserved quantities which allow one to write down the solution of this theory exactly on a piece of paper. No lattice computations required. And much of this theory has been solved by now. It's very annoying. I see your frustration. It's just too small for a clumsy hand like mine. And much of this large N theory has been solved. The complete spectrum, which is an infinite number of states, has been calculated. And maybe Nemo will discuss the completion of that, the final steps of solving that theory in the large N limit. Now, this is an incredibly useful tool, I believe, as it always has been in the history of physics. And we're just beginning to make full use of it. To go back to QCD, which is a cousin with less supersymmetry, one has to break the supersymmetry and put in quarks. That can be done, but you lose many of the nice features of the starting point. But eventually that might be one of the real ways where we will be able to analytically, on pencil and paper and not with computers, calculate properties of QCD. More interesting, it is dual to a string theory. It is believed by now by everyone that it is rigorously mathematically equivalent to string theory in a particular anti-de Sitter negative cosmological constant background. So this is not just a beautiful model anyone has looked at, falls in love with, but useful. And it already has proven to be extremely useful to a diverse set of community of physicists. It's useful for calculating QCD scattering amplitudes. Nima might discuss that. It has been useful for discovering properties, qualitative properties of the quark gluon liquid that exists when quarks are deconfined at high temperature and and large density, as in RIC, collisions of heavy ions. And it's now becoming a useful tool in many body theory. We just had a 3-month program, very exciting, at the KITP on so-called ADS-CMT, using the duality between string theory, solving Einstein's equations in some approximation, and the study of quantum critical points, which are believed perhaps to explain high-temperature superconductors. It's not only useful, I believe, but important, because the understanding of that gauge theory side of this profound duality with string theory connects to many of the deepest issues that face us in our attempts to understand quantum gravity, black holes, the Big Bang, emergent space-time, and string theory, and field theory. And the two, we're learning, are the same. So what is our framework of theoretical physics now? It's really changed, I believe, dramatically over the last 25 years. Quantum field theory, we would say. That is the basis of everything we know for sure, and it's been tested, the basis of the Standard Model. Relativistic quantum mechanics with local interactions, quantum field theory. 25, well, almost 50 years ago, 43 years ago, string theory appeared, which was believed for many years to be a revolution, different kind of theory, not based on particles or quantum fields, but on first quantized motion of extended objects. Had the possibility of unifying gravity and the other forces, and maybe answering some of those questions we face. But now we learn, but its origins, remember, were phenomenology. String theory began as a theory of open strings with quarks at the end, which indeed mimic the flux tubes we now can calculate in QCD. This is where string theory came from. It was only later that one realized that these open strings could be closed, and the closed sector had to be there, and that described gravity, and this became a theory of all the forces. But now we've discovered that the two are equivalent descriptions, these open and closed string ways of looking at things. And this is the famous duality. It's between string theory and gauge theories, where you can start with this is dangerous. You can start with branes, extended objects, membranes, and higher dimensional solitons of string theory. Good. You could start with D branes, whose low energy excitations are exactly those of gauge theories in whatever dimension you want. Let's say 4 dimensions. They also source a gravitational field in the 5th direction, and there is a limit where the gauge theory decouples, and you have an exact duality between string theory in ADS 5 cos S5 and SUN gauge theory in 4 dimensions. And it is believed that 4-dimensional n equals 4 supersymmetric gauge theory, the hydrogen atom of quantum field theory, is equivalent to 2B string theory in this background space. And that duality has been explored for the reasons to learn more about string theory, to learn more about gauge theory, to learn more about RIC experiments, to learn more about high-temperature superconductors for the last 15 years. In fact, we've learned that quantum field theory, which is our present tested conceptual framework, and string theory, this revolutionary new attempt to unify everything, are the same. They are the same. String theory is not a different theory than quantum field theory, nor is quantum field theory, or at least all the quantum field theories we know and love and the ones we believe are consistent, there's really no difference between them if you're with our present understanding. Now, of course, what that really means is we don't know what string theory or field theory is. Our understanding of this conceptual framework that we have is continuing to expand. It's a framework, like quantum field theory is a framework, not a theory. That's why we can't make predictions. That's why we can't kill it. You cannot kill quantum field theory, except perhaps by neutrinos from opera. We can't kill string theory. It's a framework. And some of the solutions, most string theorists will tell you the standard model can be written down. We don't know how to do it yet, unlike the hydrogen atom, simple case, n equals 4 supersymmetric Gauge-Mills theory. But eventually, we'll understand how to write down the standard model and any other quantum field theory, and we've learned how to do this with hundreds as a string theory. Just different ways. Yes? So we don't know what string theory is. Something is missing in a framework like this to turn it into a theory. A theory is able to make predictions, is able to be a theory like the standard model is a theory. Quantum field theory is really quantum field framework. Most likely what's missing, I believe, has to do with perhaps our understanding of space and time, most of whose properties, which are rigid, disappear in this framework. We have evidence, as in this duality between four-dimensional gauge theory, like the standard model, and string theory in 5 or 10 or 11 dimensions, that space-time in the usual sense is not a good starting point, but rather an emergent concept. We have problems with time. We're faced with a challenge. So we don't know what fixes the dynamics in this framework. What would allow us to make predictions? And that really is a cosmological problem, because we are now dealing with a theory of gravity, of dynamical space-time, therefore quantum cosmology, where we don't know. We have to determine the history of the universe, and we don't know either what the real observables are, there are very few, or what the rules are. And then we have the cosmological constant, which, as Tini said, is a problem. And it's not just the Higgs sector with a classical VEV. It's anything, any theory from quantum corrections or from phase transitions. It's preposterously small as measured and finite in theories with UV completions like string theory, so calculable and off by many orders of magnitude, which have led some of my colleagues, and now finally I can play the role of a Nobel laureate and be a curmudgeon, have led some of my colleagues to crazy ideas that we live in infinite number of possibilities and have no predictive power. We just happen to end up in the best of all possible universes, whatever the multiverse possibly could mean. So if given a minute, I will explain why we might be able to explain this. But this clearly, like radioactivity was at the turn of the century, an impossible problem at the moment. And it seems numerically kind of difficult. This is a problem for theorists, of course. I mean, we know what dark energy, dark negative pressure is, we think, a great confirmation of Einstein's theory, but the magnitude, even if you assume supersymmetry, which is the only mechanism we ever found to make the cosmological constant zero, but broken, incredibly small. But I like to argue that this shouldn't bother us, the fact that we have this small number to explain. We shouldn't start inventing multiverses. After all, we really should make this a mass ratio and not energy density. Then it's only a normal factor of 10 to the minus 16. And we've solved a larger number problem posed originally by Dirac of the proton mass to the Planck mass. Dirac was the first one to point out that this and many other numbers of this kind of order of magnitude were theoretical problems. Now, Dirac was sensible enough not to invoke anthropic arguments, which he could have easily done, because if this number were of order 1, we would be a black hole. Each of you would be a black hole, and you wouldn't be there to ask the question. And he made a prediction. He said all these numbers were related, like the size of the universe compared to the size of an atom. That changes with time, so he made predictions. Fundamental constants would change with time. You could measure that, rule out his hypothesis. But this we understand now, to within a factor of 10. And it was solved by QCD. It's the Planck mass, the proton mass is fixed by the distance at which the quarks start interacting strongly. That determines the radius of the proton. And that's determined by the logarithmic running of the coupling. So if you start at the Planck scale, unification scale, with a reasonable number like 1 over 25 for the coupling, you can calculate the size of the proton compared to the unification or Planck scale, and you get the right answer, within a factor of 10. We understand that ratio qualitatively. And we understand many other ratios, like the hierarchy of the electroweak scale to the gut scale if you assume supersymmetry, and logarithmic tricks. And we understand, we believe perhaps by the seesaw mechanism, the neutrino mass scale, which is very small. So the problem is really not that this is so small. We've done that at least 3 times, qualitatively, perhaps, we believe. Those other problems don't require the existence. Even the Higgs, the discovery of the Higgs tells us that the hierarchy problem is probably solved by the usual logarithmic trick. The problem is that in this case, unlike the other cases, we don't have a good idea. So what? We didn't have a good idea how to solve the problem of radioactivity until quantum mechanics. So with that hope or challenge, congratulations to the IFT, and thank you.
We're almost in time. I have been told by the people who are filming you that they are running out of battery in the machine. Before the question time, I want to make an announcement so that you don't escape. The announcement is that there will be a group picture taken out after we go out, and those who appear in the picture will be given a free lunch. And
thought there was no free lunch.
No, it's worth a picture. So, questions, please. Luis.
So, just a very simple question. So, do you really believe that when we understand sufficiently well the theory, it will have just a unique vacuum which corresponds to the observed world? Isn't it that as crazy as anthropic considerations, more or less? Equally likely.
Well, you see, we're asking a different question now. Once you have to construct a theory that includes gravity, you are no longer looking for a vacuum. The world around us, the world that we have observed over the last 13.7 billion years is not a vacuum. It's an evolving state. Or it could be looked at that way. I would prefer to, as Einstein taught us, the answer to the question is not a static, time-independent state, which is what particle physicists correctly looked for when they could ignore quantum gravity. That, too, is a space-time history, a rather boring one. Nothing happens. And then we do little perturbations and we see how they scatter and they come out. But what we're looking for now to be consistent, certainly with the cosmological constant whose only manifestation is the expansion of the universe, is a space-time history. All of our attempts to understand that space-time history fail, including all the so-called vacuum of string theory. As we extrapolate to the past, we extrapolate to the future, we lose observability. We no longer have any observables. Both the past and the future are shrouded in mystery. They cannot be excluded from the solution. None of those so-called vacua, the 10 to the 500, whatever, vacua are solutions of anything. They're just approximations assuming, well, let's use effective field theory for a few billion years and we won't worry about the past or the future or what it all means. I'm suspicious, very suspicious about that approach. They all might be ruled out. Furthermore, something is clearly missing. Oh, right. The only solutions we have that make sense, and there are not 10 to the 500 of those, there are an infinite number of those, are supersymmetric quantum states. For example, many different string theories in 10 dimensions in flat space, no supersymmetry breaking, absolutely consistent. We understand in strong coupling we have dual descriptions, we have an expansion, we could calculate, everything is finite, everything is totally boring. You could do experiments in those. They're observables, you do little perturbations. They do not correspond to our universe. And there are an infinite number of those. So the multiverse is like the multiverse of quantum field theory. If you say your theory is quantum field theory, you have an infinite multiverse of possibilities. Now, what we learned in science is to make other assumptions, put in other ingredients, symmetry principles, or based on observation, parameters, and describe a standard model, for example. But in the kind of extension that we've been exploring now for all these years, we don't have that possibility. We do have lots of solutions, lots of quantum states we can construct that are boring. We have effective descriptions, all of which break down in the past, 10 to the 500, who knows, which are not really solutions. And we don't know what the principle like symmetry is or how to adjust parameters to find something compelling that would be also consistent with the past, the initial state, the final state. Physics has never had to face this problem before. And we can go for generations without facing it, constructing, using string field theory models of particle physics, the next, generation of accelerators. But if we get to the region where we include gravity, as is suggested by the unification of the other forces, then we have to face up to these cosmological questions. They become physics, and you can't simply ignore them. And I suspect that when you have questions of that type that are necessary to answer, to have even imagine a complete solution that makes sense, and we have no idea how to answer them, that's the problem. That's where the problem lies. I have no idea what the solution is, but I can often identify the problem without knowing the solution.
Is there any question whose answer can only be yes or no?
Will sushi be found at the LHC?
Yes.
Any other question with a reasonable answer? Well, if not, I beg you to have your picture taken. Thank you everybody this morning once again.